Hey, Chemisters, this is Mrs. Vidalay bringing you another Blankwalle edition. So we are continuing on in section 4.6, which is precipitation reactions. So this section we're going to start off with is looking at the different kinds of reactions, and then the second part we're going to just zero in on these double replacement reactions, which will form precipitates, and how will we know? So right here in the beginning, there are 5 kinds of reactions. We have synthesis, where 2 becomes 1. We have a decomposition, where 1 becomes 2. We have a single replacement, where we have an element in a compound, makes a new compound and releases the element. Or you could do it the other way, where in this case, we have like a non-metal, like chlorine or bromine, reacting with an ionic to make the other halogen, in a sense, to become a single element then, okay? Or a double replacement, which is what you're probably going to see more of. And notice what happens. The A and the B and the X and Y, they swap partners, okay? So this is where the metal ion of one ends up with the non-metal ion of the other, and vice versa. So it says the driving force, the production of a solid, water, weak acid, or a gas. And we can talk about these being precipitation reactions. This is what we're going to zero in on for the rest of the section. And notice we have aqueous making a solid and an aqueous. Or then we have acid-base reactions, which we're going to spend a whole lot of time down in chapter 4. Okay. Finally, we have something about a combustion reaction. This is where you have like a hydrocarbon react with oxygen, and you pretty much always form carbon dioxide and water. Okay. Now, those aren't the only kind of combustions, but those are the more common ones. All right. But you can burn sodium if you want. You're going to make sodium oxide. You can burn magnesium and get magnesium oxide. So those would also be a combustion reaction. Okay. Let's go to the next page. All right, so the rest of this time is going to be on precipitation reactions, okay? So what is a precipitate? It's a solid that forms when 2 solutions are mixed, okay? So when we were back in section 4.5, we said things are soluble and insoluble, all right? What was insoluble will be the precipitate. And what's a precipitate? It's a solid. So I know it's like a whole bunch of like, what? All right, we'll try it again. So when we saw on the solubility chart that if something was formed as insoluble, that is the precipitate. What does that mean? You're forming a solid, okay? So if something was considered to be soluble, we said that remains aqueous. They remain floating in the water, okay? So this is how I do it, okay? As you're beginning, I would highly recommend doing it this way. I'll draw brackets. Do your inners and your outers. Okay, I guess I did my outers first. So look at your K and your NO3, and then look up your lead and your iodide. So go back to your solubility table from section 4.5. What do we know about all compounds that have a potassium in them? Well, guess what? They're all soluble. What does that mean? They remain aqueous. All right, so the K and the NO3 remains aqueous. What did we find out when we mixed up lead and iodide? Lead is one of those special cations that will form an insoluble precipitate with iodine and bromine and chlorine. All right, so what I just say? An insoluble precipitate. And what's a precipitate? It is a solid. Okay, so this rest of this page kind of goes in more detail of exactly what I said. So here's my Ki and my PbNO3. So here's a lot of pictures. Remember what I said about AP Chemistry. Oh boy, they love pictures, okay? So this is my Ki. Notice it's soluble. The ions have been separated. Here's my PbNO3. Again, notice this is soluble. The ions have separated. But look at the picture down below. What's going on? Look what happened. Here's my lead and my iodide that came together, all right, to form a solid. And notice that the K and the NO3 are still floating around, okay? Also notice in this lattice, you have twice as many of your, well, you really can't say that. I was gonna say you have twice as many of your iodides as you do of your leads, but you really, it doesn't show up real well, but it should, all right? So let's check out problem number 25. Okay, so does a precipitate form an aqueous potassium iodide and sodium chloride mix? All right, well, let's check this out. Let's do my outers and my inners. All right, and well, do you even really need to go back to that solubility table? Because something should strike you. Potassium is always soluble. Sodium is always soluble. So do you get a precipitate? The answer is no. All right, so let's look at problem number 26, okay? And so the next several problems are done exactly like this. All right, so what is step number one? You got to write the reactants and the products, okay? So in order to write the reactants and the products, start with your reactants, potassium carbonate and nickel chloride. Okay, let's do that. Hopefully you got something along those lines. If you're still having issues with nomenclature, come on in and we can talk about it and help you out. So you recognize this as ionic and ionic, so it's going to be a double replacement. All right, so that's when I would get out my outers and my inners. So what is the new partner for potassium? It's going to be chlorine. What is the new partner for nickel? It's going to be carbonate. So this is where, again, you need to know your charges. The charge of potassium is +1. The charge of chloride is -1, so you just get KCl. Notice it's not K2Cl2. You don't; those subscripts don't follow them. You have to know the charges and write them out. This should look familiar too, right? So what's the next thing you should always do? Balance. Go ahead and balance it. Take a little minute and balance. All right, hopefully you put a 2 here, didn't you? All right, now go back and look at your brackets. What do I notice here? I have a K. And what did I tell you will always be true for K? That means it is soluble, right? Well, what about nickel and carbonate? What does it say about nickel and carbonate? It says for carbonate, only when they're paired with lithium, sodium, potassium, or ammonium are the resulting compounds soluble. Well, what does that mean if it's nickel? It is insoluble. So what does it mean to be soluble? It dissolves. So that means it's aqueous. So you put the little AQ down there. What does it mean to be insoluble? What was our definition up here? Insoluble meant what? A precipitate is going to be formed, which means it is a solid that's going to be formed. So I'm going to put my S right here. And so that would be your entire equation. Now you could probably erase your brackets and the word soluble or insoluble and just end up with what's blue and the 2 in front and then aqueous and solid. Those need to be there. Okay, let's go to the next page. It's going to be very, very similar. All right, it says write an equation for the precipitation reaction that occurs, if any, when solutions of sodium nitrate and lithium sulfate are mixed. So go ahead and write down the correct formulas for your reactants and then see what you get. Go ahead and pause this and come back. All right, so this is what I did, and the next thing is to make your brackets. All right, and what do you notice? Here's a sodium. What do you know about all sodiums? They are always soluble. What do you know about all lithiums? Well, guess what? They are always soluble. Oh, I didn't balance it. I'm sorry. Oops, let's put a 2 here and a 2 here. Now it's balanced. I apologize. There you go. And now what? If they're soluble, it's aqueous. If it's soluble, it's aqueous. Well, did anything happen? The sodium nitrate and the lithium sulfate jump into the water. They split up into ions. Do they ever hook up and sink to the bottom? No. So really, this is all you really needed to do is write no reaction. If you ever get soluble and soluble, aqueous and aqueous, you can just write no reaction. Notice I don't even care about balancing it. There's nothing to balance. There's no reaction, okay? So let's look at problem number 28. All right, write the equation for the precipitation reaction that occurs if any when solutions of ammonium chloride and iron 2 nitrate are mixed. Go ahead and pause this. I would write your reactants and your possible products and then check out your solubilities and just see how you do. So pause this and try this whole problem from start to finish. See you in a little bit. Okay, welcome back. Hopefully you did this. So I start out here, and here are my brackets. Here's my outers and my inners. So I'm looking at the ammonium and the nitrate and the iron and the chlorine. Notice when you're doing this, iron is written first. It's your metal. So don't put CLFE. That makes no sense. Always your metal is always written first and then your non-metal. I thought maybe I'd mention that. So those are my products, ammonium nitrate and iron 2 chloride. I should probably do what else? I probably need to balance it, don't I? So let's go ahead and balance it. Hopefully you got a 2 here Na2 here. Now that's all balanced. The chlorine's balanced and the nitrates are now, everything's balanced. So what happens when you found ammonium? Hopefully you said, oh, ammonium's always soluble. Well, what else is always soluble? Nitrate is, all right? So you got a double, always, so all ammoniums and all nitrates are always. What about iron and chlorine? So what does it say? When these ions pair with silver, mercury, lead, the resulting compounds are insoluble. All right, so what does that mean? What about iron? Is iron chloride soluble or insoluble? Well, guess what? It is soluble. All right, so what does that really mean for my reaction? Well, this is aqueous and this is aqueous. Now what? You have, again, no reaction. Well, that's a bummer. I was hoping to do something fun. Why don't you go ahead and try number 29 and now see what you get. Hint, hint. Okie dokies. So did you get started with this? Here's my sodium hydroxide. Here's my copper 2 bromide. Sodium is always soluble. What does it say about hydroxide? When these ions are paired with lithium, sodium, potassium, or ammonium, well, guess what? They are always soluble. When the hydroxide pairs with calcium, strontium, or barium, the resulting compounds is slightly soluble. So what does that mean about copper? Copper wasn't on any of those lists. That means it's insoluble, all right? It says compounds containing the following ions are generally insoluble. So the copper hydroxide is insoluble. So what does that mean? If I have soluble, that means the sodium bromide is aqueous. Hopefully you've already seen several cases of that. But what about when you got insoluble? All right, what does that mean for the copper hydroxide, copper 2 hydroxide? It is a solid. So what happens? It is sinking to the bottom while the sodium and the bromide are floating around, okay? So problem number 30, again, is probably one that AP folks really like. So again, why don't you take a few minutes out, read the problem, draw your own little box and write down in pictures what's really going on. And when you're done, come back. Well, this is what I came up with. I used, 4 of everything because that's what my start was. So does that mean that here is my solid all at the bottom? That's my BX. It says that my BX was insoluble. It said that my AY was aqueous, so it's still floating around. And then it says write an equation to represent this reaction. So, oops, this is what, oh, I didn't quite get it there. This is what I did. And so what happens here, this is your aqueous and this is your solid. Hopefully that makes sense. Again, the AP loves pictures. So be aware you're going to be seeing those, okay? All right, well, I'm done. And this is the end of 4.6. You'll be practicing this. There'll be a flip quiz over this. So I hope everything makes sense for you. Fill out the WSQ and let me know if it doesn't. All right, we'll talk to you later. So don't wait to be great. Take care. Bye-bye.